Welcome everybody. In this video, we are going to derive the cross-entropy loss with respect to one of the weights of our network. Cross-entropy loss, which is this E, is the same as what it does is given a mini batch of size n, it will average the cross-entropy loss for each sample of that mini batch. And the cross-entropy loss for a single sample, E sub I, is equal to the summation over all classes of the product of T sub I, which is the true level of that class, multiplied by the logarithm of the prediction of our network for that class. T sub I, this works because T sub I is a vector of variable 0, 1 of size k. K is our number of classes. And the element j of this vector will be equal to 1 if only if this the true class of that sample is j. For example, imagine j is 0 and is 1, j equal the value of that element 0 is 1. We know that that sample y belongs to class 0. So p sub I, which is the prediction of our network, is the same as the output of our layer activated by the activation function. In this case, the activation function is the softmax activation function, which is the E y sub I divided by the summation over classes of E y sub k. And what does softmax is given a vector of size k, number of classes. After applying the softmax, each element, it will have the same dimension k, but the elements will be normalized in a way that all values will be between 0 and 1, and the summation of all the elements will be 1. So it gives us the probability of that sample I belonging to each position. So what is the prediction of, not the prediction, like the output of our layer? It's simply the dot product between the weights of our layer multiplied dot product with the output of the previous hidden layer. And we are expressing this dot product as a summation of products of elements. Now, to solve this problem, we are going to apply the chain rule because it will simplify all the steps in a way that the derivative of the whole cross-entropy function with respect to one of the weights of our network will be the same as derivative of cross-entropy function with respect prediction for that sample multiplied by the derivative of prediction of the sample with respect to the output of our layer for y sub I, the output of our layer multiplied by the output of our layer with respect to our weight. And this is the chain rule. So the first step, let's pick orange, will be doing this. So derivative of cross-entropy function with respect p sub I. This will be, it will be more clear if we derive it first with respect the cross-entropy loss of one sample, and then we will extract it for the whole mini batch. So for one sample, as we know, it's just the summation of constants multiplied by logarithm of our value. So as we know, derivative of log of x with respect to x, it's just 1 divided by x. So we will apply this. So this is the same as summation over all classes of the label of that element of that class multiplied by 1 divided p sub I. The second step is deriving p sub I with respect to y sub I. So the derivative of pi sub I with respect y sub I is the same as the derivative of e to the power of y sub I summation over k. I'm just writing the sum activation function, e to the power y sub k with respect now, yes, of y sub I. So here we have a problem with the indexes, so I'm going to replace this y by j, so there's no confusion among them. what happens here? As we know, this y and this j may reference the same element or not. So we're gonna do two cases here. So case 1, y equals j. So in this case, let's derive this. I'm gonna rewrite this function as a multiplication, as a product. So it's just simply this summation over k e y sub k to the minus 1. For me, it's more clear when I apply the product rule. So the derivative of this is derivative of the first term, and because y equals j, it stays there. So this is the same as e y sub I multiplied by the rest, k e y sub k to the minus 1. Now, plus, because it's the product rule of the first element, and now we are going to apply the chain rule to derive this. So we have this minus 1 goes down, then we have minus 2 of the same thing here, okay, plus the derivative of what it is inside. Now, what's inside here? Here is a summation over all classes of e y sub k. So this is the same as e y sub 1 plus e y sub 2, well, 0, starting by 0. So all these are constants except when one of these elements is j. The rest will be treated as constant, so its derivative will be 0. So here we will have summation over k of e y sub k. We are applying the chain rule we just did, minus 2. The minus 1 we had here goes in front, so this plus becomes a minus. And now we multiply here the derivative of what's inside here. And as we said, this is just a summation of elements, and all of them are constants, except the case when k equals j. So e y equals sub j. Now, let's keep simplifying this expression. This is the same as e y sub I divided by summation over k of e y sub k. I just put this as a division, minus e y sub I multiplied by e y sub j divided by summation over k e y sub k squared. Now, we are gonna make a common denominator to unify this subtraction. So to make the same denominator, we have to multiply this by itself to make it a square. So we are gonna multiply the same denominator by the same element. So this is e y sub I multiplied by summation over k e y sub k. Now yes, divided by summation over k e y sub k squared minus e y sub I e y sub j. We just unified the whole division. Now we see that e y sub I is in both terms, so we are gonna extract it. So this becomes e y sub I that multiplies summation over k e y sub k minus e to the power y sub j. So this element is outside the summation. Now this is divided by the same thing squared, like this element. So now we are gonna split this product between two, so we have e y sub I divided by summation over k e to the power y sub k multiplied by summation over k e y sub k minus e y sub j divided summation over k e y sub k. Okay, so here we see that this first term is the softmax activation of I. So this becomes p sub I multiplied by this whole thing. This whole thing, as we may see, let's do it here to just not write the whole thing again, is the same as summation over k e y sub k divided by summation over k e y sub k minus e y sub j, this was a j, divided by summation over k e y sub k. So as we can see here, this becomes 1 because it's an element divided by itself, minus softmax activation of element of class j, sorry, because there are not elements in the mini batch but classes, because we are deriving with respect to a single sample. So this whole thing becomes 1 minus p sub j. And this is the derivative of p sub I with respect y sub j when I equals j. Now let's do the second case, case 2, which is when I is different from j. So in this case, let's write derivative of ey sub I summation over k ey sub k with respect to y sub j is the same as, and as we did before, I'm going to express this as a multiplication, ey sub I multiplied by summation over k ey sub k minus 1 with respect to y sub j. So now this element and this element are not the same, so it's just like a constant. So when we apply the product rule, this first term will become 0 multiplied by this whole thing, so it's 0, plus the first element. As we did before, we're going to apply chain rule to this whole thing, so minus 1 goes down here, so this becomes a minus. So this becomes minus 2 of summation over k ey sub k multiplied by e to the power y sub j. This is, as we said before, because this is a summation of constants except the case when k equals j. So we're going to express this as the product of e y sub I e to the power y sub j, sorry, this is power y sub a, divided by summation over k of e y sub k squared. Now we can split this into minus e y sub j divided by summation over k e y sub k multiplied by e y sub I summation over k e y sub k, and this becomes minus prediction of j, prediction of y. So let's recap here, and we have that the derivative of pi sub I with respect y sub j, p sub I with respect y sub j is equal to p sub I 1 minus p sub j when e equals j, which is the case 1, and it becomes minus pj multiplied by pi when e is different from j. Now let's do the final step, which is derivative of y sub I with respect our weight. So derivative of y sub I with respect the value ji. So this is the derivative of summation of h sub j multiplied over all classes multiplied by the value ji with respect the value ji, and this is just h sub j. So we are now finally ready to compute the whole derivative. So let's write again the chain rule expression with respect to one of our weights is the same as derivative of the cost function of that sample with respect the prediction multiplied derivative of the prediction with respect to the output of the layer multiplied by output of the layer with respect to our weight. So let's do first this part and then we're gonna add this final part. So this becomes, remember this first derivative was just summation, let's get it. This first part was summation over k ti 1 divided pi, so minus summation over k ti divided by 1 over pi. And this derivative was pj divided by y sub j equals to pi 1 minus pj if e equals j, and it was minus pj pi if i different from j. So this product becomes this multiplied by this. So we need to, there are two cases here, when y equals j and when I equals not equals j. So let's rewrite this different. In this summation, when k equals I, it will multiply by this. So we have ti multiplied by 1 pi minus, multiplied by pi 1 minus pi, and the rest will be summation over k when k is different from I, right? Because when k is equal to I, it's written here. We just this is a summation over all k, so we took when k equals I, we extracted outside, and we are doing the summation over all the other elements. It was just that. This will become t sub k 1 over pk. And we are changing the indexes again because to not get confused. Multiplied when pj for pj pi. Sorry. pk pi. Now if we do this product, remember we are just computing this part. Then we will multiply by this. If we compute this, it becomes so these two elements go away, so this becomes minus ti multiplied by 1 minus pi minus summation over all k except when it is equal to I of tk 1 over pk p sub k, p sub k multiplied by p sub k p sub I, and is equal to minus t sub I multiplied by 1 minus p sub I minus summation over all k except when k equals y of, and we can, this goes with this, and then we have minus tk pi, but we can extract, so this is the same as having minus 1 multiplying to the whole thing. We can extract this minus 1 to outside the summation, so we can put plus here and remove this here just to get rid of that minus. And finally, it's the same as having p sub I, because this p sub I doesn't depend on k, we can also extract it outside here, so we have p sub I here, and we can remove it from here, and we have t sub k only, right? This is like having summation over I of 3 p sub I. This 3 you can put it outside, right? So finally we have this p sub I, we see a p sub I here and a p sub I here, so this is the same as having p sub I multiplying this t sub I multiplied by 1 is minus t sub I, but so basically what we do here first is this minus 1 we put it inside, so we have minus 1 plus p sub I. And after this we extract this p sub I, which is multiplying at both sides here, and then we have t sub I, exactly because t sub I plus summation over all classes except I of t sub k minus, okay. And finally we get this, which is the same as p sub I minus ti. And this is because basically, as we said before, t is a vector of with 1 1 and the rest zeros. So the summation of 1 plus 0 plus 0 blah blah, it will be equal to 1. And this here is the summation of all the elements of t. So this will be equal to 1. So we have p multiplied by 1 minus t sub I. So this was the first part, this here. So if we go back and we replace this part with this result, we obtain that derivative of e sub I with respect j sub I, wh sub I, is the same as p sub I minus t sub I multiplied by derivative of y sub I with respect w j sub I, which we said that was h sub j. And this is the derivative of the cross-entropy loss of one sample with respect of that weight. So if we want to do it for all the samples, the only thing we will need to do is average this for all the samples. So let's remember that the whole cross-entropy loss for the mini batch, it was 1 over n summation over y to n of cross-entropy loss of the single sample. So cross-entropy loss, the derivative of the cross-entropy loss with respect to weight will be with respect our weight will be 1 over n summation over n of p sub I minus ti hj. And that's our result.